All right, so it seems to be 2:30, so maybe let's go ahead and get started. So it's my great pleasure to introduce our next speaker. So Juliette Bruce is currently an NSF postdoctoral fellow at UC Berkeley. She is a postdoctoral fellow also at MSRI with research interests in algebraic geometry, commutative algebra, and arithmetic geometry. She received her PhD from the University of Wisconsin-Madison in 2020 under the direction of Daniel Ehrman. And she has been involved over the years with many LGBTQ plus initiatives, including being the founder of Out in STEM, the chapter at the University of Wisconsin-Madison, an organizer and participant in many Spectra events, as well as organizer of the LGBTQ graduate student group at University of Wisconsin-Madison. She will be telling us today about computing syzygies.
Thank you so much for that lovely introduction, and thank you all for taking the time to be here with me today. As said, the mathematical portion of my talk is going to be about computing syzygies, and all of the math I'll talk about today is joint work with Daniel Ehrman and Stephen Goldstein, both of whom are at the University of Wisconsin-Madison. And it is also joint with Jie Yang, who is a postdoc at the University of Minnesota and who is also on the job market this year. But before I turn to kind of the mathematical things I want to talk about today, I want to take a minute to kind of give a few acknowledgements and kind of set the stage for, I think, what kind of the space we're sitting in. So where I work and live occupies the ancestral and current homelands of the Mukema Ohlone tribe and other familial descendants of the sovereign Verona Band of Alameda County. Black and Indigenous lives matter. Further, where I live and work is only a few miles away from the site of Gene Compton's cafeteria, where 54 years ago, in the face of transphobia, police violence, and state violence, one of the first actions in the modern LGBTQ movement occurred, led by Black, Brown, and Indigenous trans women. I want to also kind of take a minute to recognize and hold space for the fact that this week is Trans Week of Visibility, and in particular, tomorrow is Trans Day of Remembrance. And so I want to take a second to hold space for all the trans people, all the people in the trans community and all the struggles they might go through, while also holding in our memory kind of the power we can draw from looking back on our ancestors who have kind of fought this fight long before us. Okay, thank you. And I'll end this title slide by just again reiterating that Black and Indigenous LGBTQ lives matter. Okay. So a bit about myself. So again, my name is Juliette Bruce, and I'm a National Science Foundation postdoctoral fellow at the University of California, Berkeley. I'm also in residence at the Mathematical Sciences Research Institute, also in Berkeley, California for the year. Prior to coming to the Bay Area, I spent all of my life in the Midwest. So I did my graduate work at the University of Wisconsin-Madison. And before that, I did my undergraduate degree in the University of Michigan in Ann Arbor, where I majored in both mathematics and political science. And I think this year has certainly made it clear that I made a good choice by avoiding political science after this. And before that, I grew up in the middle of a cornfield somewhere in rural Michigan. And here are two photos of me, one where I'm very put together and one where I'm dying, having run halfway up the Eiger and are contemplating the fact I have half left to go. I also wanted to kind of begin to help set the stage for today and kind of the space by reading two quotes. One, which is very personal and moving to me and my relationship to the LGBTQ community, and one which I think is going to help set the stage for the mathematics I want to talk about. So eventually, you can't help but figure out that while gender is a construct, so are traffic lights. And if you ignore either of them, you get hit by cars, which also are constructs. And this is a quote by Imogen Binney from the book Nevada, and it's something that's kind of shaped my life in many ways, and certainly shaped my relationship to the LGBT community in many ways. And the second quote, the more mathematical of the two, is that mathematics is the cheapest science. Unlike physics or chemistry, it does not require any expensive equipment. All one needs for mathematics is a pencil and paper. And this is by George Poilea in 1985. So not all that long ago. And part of what I want to talk about today is kind of a project that I think is really fun because it kind of runs counter to this quote. So my field is algebraic geometry, which in many ways is kind of in the heart of theoretical pure mathematics. And I think if you asked most algebraic geometers, including many of the experts in the audience, they would agree that most of their days are spent, as Poilea describes, with pencil and paper, or now maybe Zoom and a tablet doing work. I see David holding up paper and pencil even now. And so the idea behind this project is that if we sometimes behave like other scientists, like physicists or chemists, and we kind of throw massive experimentation and massive resources at problems, we can generate interesting data that can help us with theoretical math. Okay, let's see. Okay, so now let's get into the math proper, and let me introduce the star players of today's show. The first are algebraic varieties. So an algebraic variety is just a fancy name for the solution set to a system of polynomial equations. So sometime in your mathematical career, you probably learned about how to solve a system of linear equations by plotting them in the plane and seeing where the lines intersect, or by reduced row echeloning some matrices. You might have even learned how to solve a system of quadratic polynomials via the quadratic formula, things like that. And really, algebraic geometry, the field I'm interested in, is kind of a souped up version of this, where we want to study the solution set to a system of many polynomials and many unknowns, and try to relate the geometry of the solution set to the equations and the algebra that we get in the equation. So here I have a picture of what's called the thistle or distal, depending on which language you speak, which is the zero set of this polynomial in the right-hand corner here. And so the idea behind algebraic geometry would really broadly be to ask, what can I tell about the geometric properties of the surface? For example, why are there these 6 pointy points? From just looking at this algebraic equation, this algebraic polynomial. So that's one player, namely the zero sets of a system of polynomial equations. The other player is syzygies. And before I get to the mathematical kind of origin of syzygies, I kind of want to, I'll step back and say, where does the word syzygy comes from? It comes to mathematics via astronomy. And an astronomical syzygy is when 3 or more astronomical bodies, planets, suns, moons, etc., are roughly collinear. And the idea is that if you have 3 heavenly bodies moving about space, you do not expect them in general to lie on a line. That would be something that's very special, and there would be a special relationship in time and space that we want to take note of. And mathematical syzygies are something similar, which is they are special relationships that in algebraic geometry we want to kind of take note of if we really want to understand the geometry and the connection between the geometry of variety and the algebra it's defined by. Okay, so slightly more precisely, a syzygy is just a polynomial relationship amongst a collection of polynomials. So that's a little bit of a vague definition, I will grant you that. But I don't think it's, for this talk, it's not important to necessarily give the precise one. Instead, I think it's better to intuit what I mean here when I say a polynomial relation amongst a collection of polynomials. And the best way to do that is via an example. Okay, so the example I want to consider is the set of monomials of degree 3 on 2 variables, namely the variables s and t. So I have my collection of polynomials is just 4 monomials, namely s cubed, s squared t, st squared, and t cubed. So these are this is a collection of polynomials. And then I want to, when I talk about syzygies, what I want to do is look at all of the possible polynomial relationships amongst these 4 monomials. And what do I mean by a polynomial relationship? Well, if I take the first one and multiply it by the third one, I get the second one squared, right? So kind of written out formally, s cubed times st squared minus the square of s squared t is equal to 0. And likewise, if I take the last one and I take the second one and I multiply them together, I get the square of the third one. which again just can be written here as the second equation, that s squared t times t cubed minus the square of st squared equals 0. And finally, if you do the product of the first and the last, you get the product of the middle. So t cubed times s squared, or t cubed times s cubed minus s squared t st squared is equal to 0. And so these are relations in that there's some polynomial expression in my variables s and t which equals 0. An easier way to look at these sometimes is to do a slight change of coordinates. So instead of looking at s's and t's, if I let x be s cubed, y be s squared t, z be st squared, and w be t cubed, and I make a substitution here, what we see is we get three nice polynomial equations that are set to 0. Namely, we get xz minus y squared equals 0, yw minus z squared equals 0, and xw minus yz equals 0. And these are what we call the 0th syzygies, because these are the 0th set of polynomial relations amongst the monomials of degree 3 on 2 variables. You might ask, are there other polynomial relations we could consider? And the answer is, of course. If I took any of these polynomials on the left here and multiplied them by something, that expression would stay 0. And if I add any of these expressions here, it also remains 0, because 0 plus 0 is 0. So somehow I actually kind of have a vector space or a module of such things. But these three I've written down here are fundamental in that they kind of form a basis for the space of all possible syzygies. So F1, F2, and F3 here are kind of the fundamental 0th syzygies we'd want to concern if we're looking at just the monomials of degree 3 on 2 variables. Okay, so those are the 0th syzygies, but the real name of the game, the idea behind syzygies in algebraic geometry is you don't stop there. You want to keep going. So instead of looking at just the relations, we now need to look at the relations amongst the relations, which are called the first syzygies. And doing that, we see that z times f1 plus x times f2 minus y times f3 is equal to 0. And likewise, wf1 plus yf2 minus zf3 is equal to 0. And so these two relationships here are first syzygies. They're first syzygies because they're relations amongst my 0th syzygies. So they're relations amongst the relations. Once again, you can check that these are polynomial relations, in this case, the x, y, z, and w. And further, you can show that these two are kind of the fundamental ones, the ones that form a basis for the space of all first syzygies. And now we'd play the game one more time. We look at the relations amongst the relations amongst the relations. So what are the relations here? And it turns out that, with not too hard to show, that you can see that these two polynomials are going to be independent and have no non-trivial relations amongst them, which means this game stops at the first step. But a priori, you could imagine that if I gave you some collection of polynomials, you could have to take 10 or 20 or 30 or 50 or however many steps you might need until this game stops. Okay? And so this is the idea behind a syzygy, which is we're just giving you a collection of polynomials, and you want to find all the relations, and then the relations on the relations, and the relations on the relations on the relations, and so on. And I said that somehow these syzygies are capturing something geometric. And so what's going on in this example? Well, in this example, these 4 monomials that I've written here in my set actually parameterize this green curve in the picture in the lower right-hand corner, which is called the twisted cubic. And finding the 0th syzygies essentially tells me that I can write this green curve as the intersection of these 3 surfaces, which I've kind of depicted here. So really, somehow, this first syzygies are kind of giving us defining equations that cut out some geometric object. And it turns out the first syzygies tell us even more if we cared to study them. And so this is kind of an example that hopefully gives you a flavor for what I mean when I say talking about the syzygies of kind of an algebraic variety or a collection of polynomials. And we could ask about this game more generally. So right there, we did the syzygies amongst the monomials of degree 3 in 2 variables. And we could ask whether we could do this game of looking at the syzygies amongst the set of monomials of degree d and end variables, right? So you could write down all the monomials of degree 15 and 17 variables. There'd be a lot of them, and then you could try to find all the possible relations amongst these. This turns out to be a really central question, kind of in algebraic geometry, or at least my heart of algebraic geometry, and turns out to be one that is very wide open. So here I've made a chart where the columns represent the number of variables and the rows represent the degrees of monomials I'm taking. And everywhere you see a green check mark is a place where we know all of the syzygies. Every place you see a red check or red X is a case we don't know anything. And the purple checks and squiggles are where I want to talk about today. So the first thing you might notice is that if we're working with just two monomials, like we did before in the previous example, things are pretty well known. In fact, we know the syzygies of the monomials of degree d and two variables for all d. So any number of degrees, we worked out 3 there. In general, you could work them out. It turns out to be a little more complicated, but really it's not too bad. For the experts in the room, what's going on is that with 2 variables, I'm looking at the rational normal curve of degree d. That's given by the minors of some matrix, and the minors of this matrix happen to be resolved by an Egan-Northcott complex. So we can explicitly write down the minimal graded free resolution. But in general, once we move past the land of 2 variables to 3, 4, or 5 variables, things become hopelessly complicated. So for example, even if we're looking at just 3 variables, we only know the syzygies when we're looking at monomials of degree 3, 4, or 5, and then the rest of this talk will be telling you how can we find those syzygies when the monomials have degree 6, 7, or maybe 8. And what I want to highlight here is that the reason we see this bifurcation in this table in part is that when we're looking at just 2 monomials, what we're really considering is the case of an algebraic curve. And this is something that's very classical, that begins kind of its study with Emmy Noether and continues through the 20th century with people like Mark Green and Rob Lazarsfeld and David Eisenbud. And there are beautiful conjectures and results, including Poisson's work on generic Green's conjecture, kind of talking about the syzygies of curves. But it turns out that once we start looking at the syzygies of higher dimensional algebraic varieties, so surfaces or threefolds, we just have much less of an understanding for how things behave. And in fact, we have some sense that things behave in extremely complicated ways that we just don't understand yet. But we know they have to be complicated. And so the rest of today's talk will be kind of challenging Polya's idea that you shouldn't do this, you shouldn't behave like other scientists in mathematics, and instead saying that if we behave like physicists or chemists and throw a lot of computational power at this problem of computing syzygies of monomials and 3 variables, we can generate new data, new examples that will tell us and give us a way forward mathematically. Okay, and before I go into the next slide, I'll just quickly note that for the experts, what's going on geometrically is I'm taking the projective n-1 space, where n is the number of monomials, and I'm embedding it into some big ambient space by the Veronese map of degree d, and then I'm looking at the syzygies of the defining equation. So I'm basically saying here, we understand the syzygies of the rational normal curve, but not of the projective plane, and not of projective 3 space or 4 space, and so on. Okay. So again, we're going to focus on this case of 3 variables for the rest of the talk. And it turns out that if you tried to do this by hand, you'd quickly give up. So I think by time you're looking at 3 variables and d is 4, there's going to be 50 to 60 different 0th syzygies, and so you just won't want to do this by hand. So instead, you might turn to your standard computer algebra software, something like Sage or Singular or Macaulay 2 or Mathematica or whatever you like, and ask it to compute the syzygies. And many of those languages have great internal algorithms for doing this via something called Grosvenor bases. But it turns out these algorithms just bog down extremely quickly once you're outside of the case of curves. Okay, so for example, once you're looking at 3 variables in degree 5, Macaulay 2 or Sage or Singular is not going to get you all the syzygies. And the reason is kind of this curse of dimensionality, which is when you're working in higher dimensions, the number of things you're working with, the complexity starts growing instead of linearly in D, but grows quadratically or cubically or something even worse in D. But it turns out that we're a little bit saved in that we can convert the question of computing syzygies from one of kind of algebraic geometry, into one of linear algebra. Really, the question of computing syzygies is the same as computing certain causal cohomology groups, which is the same as just computing the ranks of certain matrices. So if I want to compute all the syzygies for 3 variables of, say, degree 6, all I have to do is write down some matrices, there's maybe 30 of them, and compute their ranks. This is not something new. This has been known to experts in the field for a long time, but no one, I think, ever tried to do anything with this fact, because you quickly learn that the matrices you'd have to compute the ranks of are too big to actually do anything of use with. So for example, one of the matrices you'd have to compute the rank of is 254,103,788,400 by 902,737,143,000 columns wide. So this is something that if you just tried to load into Mathematica or MATLAB, you will likely crash if you even somehow manage to write it. And even if you manage to write this matrix to memory, there is no way in the world you will ever get a standard off-the-stock rank computation to run on a matrix of this size. It's just outside of our current realm of computation ability. That said, it turns out that this problem has a lot of really deep underlying symmetries coming from certain multigradings, if you know what those are. That means these huge matrices that are billions by billions wide can be broken down into a large number of just big matrices. So for example, we could take this matrix I've written up here and break it into something that would reduce the problem to computing the ranks of roughly 1,700 matrices, with the largest being roughly 4 million by 12 million big. So a 4 million by 12 million matrix seems bigger than any mathematician would ever do with pencil and paper. And that's fine, because we're not going to behave like most kind of pure mathematicians, and instead we're going to throw all the computational power we can at this problem to see if we can't compute the ranks of this 1,700 matrices that are millions by millions wide. Okay. And it turns out that you can, but you have to be clever in some ways, or at least you have to be what we think of as clever, not being applied mathematicians. So as pure mathematicians, being clever in this case means we have to leverage advances in sparse numerical linear algebra. So these matrices, while huge, tend to have relatively few non-zero entries. And so we can ask our applied math friends to very generously help us compute their ranks using things like a sparse QR decomposition or a sparse LU decomposition to get approximations of the ranks of these matrices. The next issue to overcome is, again, there's 2,000 of them, and they're pretty big, so you definitely don't want to run them sequentially on one computer. In fact, they won't run on most computers you have in your department or in your house. For example, one small part of a computation for the degree 6 monomials in 3 variables, I've kind of outlined how much computational resources it needs in the table at the bottom. So you see that most matrices run pretty quickly, so in a matter of minutes, and don't take that much memory, but there are a number of them that take hours or half days or even multiple days long and require 10, 20, 500 plus gigabytes of memory. And to give you a sense for what this means, most kind of desktop or laptop computers have at most 32 to 64 gigabytes of memory. So you are not even going to compute your laptop would not even do all of these computations if you tried. So really, it's important that we behave like, that we take advantage of kind of these huge computational networks that have developed for computational scientists and distribute our computations across hundreds or thousands of computers, including many high performance nodes, so that we can run things in parallel. And this tends to be exactly what physicists and other scientists do, right? With things like the LHC or LIGO, they take their computations and send them all over the world. And so for our special little problem of computing syzygies, we tried to do the same. And hitting everything with all of this in this way, the problem really becomes one of bookkeeping and keeping everything in order. And doing this, we're able to actually compute the syzygies of the monomials of degree 6, 7, and some of 8 in 3 variables. And we computed a lot of additional data I'm not telling you. So for example, we computed all the syzygies of the associated push forwards. We computed all the Schur-Veronese syzygies, the multigraded syzygies, and a bunch of other data. And then all of it's available both at syzygydata.com and also via a Macaulay 2 package that will be available soon. And this, I think, is a really interesting project and kind of a test case for what can be done when you set aside the paper and pencil. But I also think this data we generated actually suggests some really interesting conjectures and some really interesting things are going on in the case of higher dimensional syzygies. So I said curves were well understood. The game for surfaces is very wide open, but our data seems to provide evidence for a number of existing conjectures and also suggests there are deep symmetries that are controlled in some cases by some very special syzygies. Okay, so as an example of one of these conjectures that our data provides evidence for, Ein, Ehrman, and Lazarsfeld have a conjecture that essentially says if you count the number of syzygies in a special way, that number of syzygies should look roughly like a normal distribution. And lo and behold, if you plot the number of syzygies counted in this special way for the monomials of degree 3 on 6 of monomials on 3 variables of degree 6, you get exactly what looks to be a normal distribution. Okay, and there's a lot more I think that could be said in this data, and I think this data set is there to kind of dig through for anyone who wants to find conjectures. But I also think that in some ways, right, we are doing the simplest possible higher dimensional case you can do. We're doing the projective plane, we're doing just monomials. You could imagine doing things that are more complicated, so more general sets of polynomials, and ask what the syzygies behave there. And the answer is that if it's in higher dimensions, while there are some very lovely results, in general, things are extremely wide open. And so you might ask about what do the syzygies of P1 cross P1 look like, or what about the syzygies of Hirzebruch surfaces or elliptic surfaces? And the answer is that it's wide open because the number of examples we have for each of these things is probably counted on one hand. And I think there's a lot to be learned and a lot of low-hanging fruit that could be had just by running this game of using huge amounts of computational power to generate new data to kind of show us what should be true kind of in this very stuffy, pure area of mathematics called algebraic geometry. Okay, and so I'll end here, but I'll end with a few notes. First, I want to say that some of you might be looking forward to a few other events I'm involved with. So one being Trans Math Day, which is happening online in a couple weeks. The other being SpecQBar, a conference for LGBTQ mathematicians in algebra, geometry, and related number theory and related fields, that is also being graciously hosted by the Fields Institute and is scheduled for the summer of 2021. And it was all being hosted or co-organized with a number of great people. And I'll end by saying, if you've never heard of syzygies in a mathematical context, but you are a big Dykes to Watch Out fan, so you like Alison Bechtel, an amazing LGBTQ cartoonist and originator of the term the Bechtel test, here is a great comic strip where the word syzygy comes up. So I'll end here and thank you all for spending time with me today.
Great, thank you, Juliette, for the great talk. If everyone could proceed to unmute themselves. Let's thank Juliette again.
Thank you.